Hey everybody, Missy here, and today we're going to learn about nuclear reactions, fission, and fusion. For our notes today, we're going to use our periodic tables, so go ahead and open that up in another tab or get yours out. They're going to be helpful for us to do some of our practice problems together today on nuclear reactions. So remember back to our video notes from last time where we talked about that nuclear chemistry happens inside my nucleus. And we've also talked about inside our nucleus is where all the mass of an atom is. And in fact, we can calculate the mass number of something by looking at the number of protons plus our number of neutrons. The other thing we have is when we write the symbol for an atom, we always have our mass number on top of our atomic number. And then we have our symbol after that. We're going to use this to write nuclear reactions today. In a nuclear reaction, the mass number and nuclear charge are conserved. The mass number is the number on top. The nuclear charge is our number of protons, which is also equals the atomic number. Okay, so mass number and atomic number are conserved, which are my protons in my nucleus. Okay. They either have absorption or emission of nuclear particles, and we talked about that a little bit last time. During the reaction, energy will also either be absorbed or released depending upon what was happening with my nuclei. We have two types of reactions. We can have an example of fission or fusion, are the ones that we're going to default to looking at. Are things coming together or is one thing breaking apart? Fission, which is what we'll start with. Fission is where the nucleus of an atom splits into two smaller parts. So we can see that we have our uranium-235 and that it's getting hit by a neutron. That neutron hits it and then it forces it to explode and split. So we have a nuclear collision. It gives off energy in terms of gamma rays. So it splits apart. When it splits, it also releases some neutrons. And then the new nuclei that we make, we call them daughter atoms or daughter nuclei. And we can see that from this uranium, we have made a 90/38 SR, which is strontium, and a 143/54 Xe, which is xenon. So for my uranium, I have now made strontium and xenon. This is used around us already, thanks to it releasing so much energy, which you can see from the little lightning bolts here. We use this reaction of fission in power plants, okay, which can help create power for an area. They mainly use uranium-235, but can also use polonium. And this is also what was used in the atomic bomb. That mass amount of energy that was given off when the atoms split, that's what causes that atomic bomb to have such a profound impact on an area. And then, because it gives off so much energy, and these are gamma rays, we learned that that's radiation. And that's why there's that radiation or the fallout that happens after an atomic bomb is dropped. Then we have fusion. Fusion is the opposite of fission. Fusion is two small nuclei coming together to form one larger nuclei. And we can see that here we have this little guy is called deuterium, and this little one is called tritium. They are going to get smashed together, so they're going to kind of hit at the same point here. When they hit together, they also release energy. So they release lots and lots of energy. In fact, it's more energy than fission. Okay, more energy is given off in fusion than fission. When, in this case, these two nuclei collide, they make a helium, which is also an alpha particle, and a neutron plus energy. Now, fusion currently is really hard to do. We're not great at it. But we have places like the Hadron Collider and CERN and the Fermi Lab who are trying their best to analyze, it's called particle physics, where they are looking to see how can they make this happen easier and more cost efficient, because there are no byproducts that are bad radiation from fusion. It gives off a neutron that's neutral, and it gives off a helium atom. And we learned that helium atoms are alpha radiation, and they're pretty harmful. Unless you actually eat it, it's not really going to hurt you. And so we're trying to figure out, well, how can we use fusion because it's less dangerous? There's no radioactive fallout. There's no harmful elements here. How can we use that to better help us? This is also what happens in the sun. So also what happens in the sun. So the sun takes deuterium and tritium, they collide, produces energy, which is that lovely heat that you feel from the sun, and then we give off a helium and a neutron. Then that helium eventually gets split and then turns back into deuterium and tritium. So let's go through some examples of actual nuclear reactions. To do this, this is where you're going to need your periodic table. So we can see that we have sulfur 32, a blank space, 01E, which we remember from last time is 01 negative E is our beta particle. We need to write down our atomic number for sulfur. We do that by looking at the periodic table. Periodic table, remember our numbers in the upper left-hand corner are the atomic numbers. So for sulfur, my atomic number is 16. So I write 16 underneath. We said mass number is conserved, charge is conserved. So if my mass number is conserved, that means that my numbers on the top on the right add up to equal my numbers on the top on the left. Same thing for the bottom numbers. My numbers on the bottom on the right have to equal my numbers on the bottom at the left. Excuse me. So if my total number on the top on the left is 32, I have 0 here. So that means this must also be 32 because 32 plus 0 is 32. Then on the bottom, on the left, I have 16. Here I have negative 1. Well, what plus negative 1 is 16? That's 17, right? 17 minus 1 is 16. To figure out what element I have here, I look to the periodic table and figure out what is element number 17. On my periodic table, element number 17 is chlorine, Cl. So I write Cl. That was one atom splitting into smaller atoms. So we say that that is fission. Because we have splitting. Specifically, it is giving off a beta particle. So we say beta emission. Because it is giving off a beta particle. To translate this into words, we would say that sulfur 32 decays by beta emission, because it gives off a beta particle. Oops. ION. Yikes. By beta emission to make, we made chlorine 32. Okay. My next one, I have O and N. O is oxygen. We need to look at its atomic number. Oxygen's atomic number is 8. So we put the 8 there. Nitrogen. Nitrogen's atomic number is 7. Then we need to fill in our missing particle. Charge is conserved and mass number is conserved. So our mass number on the left is 14. On the right, it's 14. So that means something plus 14 is 14. That must be 0. On the bottom, I have an 8 here and a 7 here. Something plus 7 has to equal 8, which is 1. And I look to my my particles, and I see that the one that is 0 over 1 is my positron. So 0 over 1e. So that's what I write. We have, again, emitted a particle, and we said this was a positron. So we have split our nucleus. So it's fission. Specifically, it is positron emission. And if we were to write this as a sentence, we would say that oxygen 14 decays by positron emission to make, and it makes nitrogen 14. Now we have our last one. Our last one, we need to again figure out what is our atomic number for Pu. So we look on our periodic table to find Pu, and I haven't looked ahead of making this video, so let's see if we can find it. Here it is, plutonium, number 94. So plutonium, 94. You can see that I have my alpha particle here. My mass has to be conserved. I have 242 here, 4 there. So I need to have 238 on the left, because 238 plus 4 is 242. On the left, I have 94. On the right, I have 2. So this must be 92 plus 2 is 94. And I need to figure out what is element number 92. Element number 92 is uranium, letter U. So uranium. Again, we're splitting atoms, so we have fission. And specifically, we are giving off a helium atom, which is an alpha particle. So I have alpha emission. If I were to write this in a sentence, I would say plutonium, plutonium, plutonium 242, its mass number, decays by alpha emission to make uranium 238. So now you're able to write nuclear reactions.